This is the second video of the second half of week 1 of this module, ST342, Mathematics of Random Events. We will start defining and discussing properties of the sigma algebra generated by a certain class of sets, and then we discuss the Borel sets, which is a particular case of the sigma algebra generated by the Borel sets. Let us start discussing what the generated sigma algebras are, and the definition is the following. Here, this calligraphic E, it represents any class of subsets of omega. It could be any class, could be empty, it could be the class of all subsets of omega. There's no structure assumed about E, except that the elements of E are subsets of omega. So we define the sigma algebra generated by E, which is denoted sigma of E, as the unique class of subsets of omega that have the following property. The first property is the sigma E here that we are defining. It is a sigma algebra. The second property is it is a sigma algebra that contains E. And the third property is any other sigma algebra that also contains E must contain this sigma E that we are defining now. So in this sense, since it contains E and it must be contained in any other sigma algebra that contains E, so sigma of E, we can think of it as the smallest sigma algebra that contains E. So this definition is not complete in its own because it talks about the unique class satisfying these three properties, but it is okay to define it this way because there is a proposition here. Proposition says such a family indeed exists and indeed is unique. So there exists a class satisfying those three properties, and it's a unique, there is no other class satisfying those properties. If there's another class satisfying those three properties, it is the same. And the proof of this proposition, the proof is given in the lecture notes in the form of a guided exercise. So there are several steps to be completed, and in the lecture notes we mention those steps one by one, and you are supposed to fill in the gaps and show each of the parts of the proof as following the guide as provided in the lecture notes. How do we use this definition? Here's a very simple example. We have a sample space and we have a subset of this sample space. Let's call the subset A, and consider the class of subsets of omega that has only one element in it. It has only this set A. And the claim is the sigma algebra generated by this class E is this one here. It's a sigma algebra A, calligraphic, which contain the empty set. It has the empty set, it has the entire sample space in it, it has the set A, and it also has the complement of A. And now how can we justify from the definition that the sigma algebra generated by this class is this one? Well, we have to check that this family here satisfies those three properties. First, it is a sigma algebra. Yes, it is. Yeah, we can check this is a sigma algebra. It contains E. Yes, it does contain E because E only has this element and this element is here. And any sigma algebra that contains E, it must contain A. How can we prove that? Well, if a sigma algebra contains E, because it's a sigma algebra, it must have omega. And because if it's a sigma algebra, it must have the complement of omega, which is empty. And because it contains this calligraphic A here, it must have A. But then because it's a sigma algebra, it also must have its complement, A complement. So we have just proved that any sigma algebra that contains E must contain these four sets, which means it contains A. So we just checked first property, second property, third property defining what is the sigma algebra generated by a class. Here is a second example which is just developed from the first example, which is the following. Suppose the class E, it has these n sets in it, and these sets, they form a partition of the sample space omega. So they are disjoint and their union equal omega. That's what it means to be a partition. Then we claim that the sigma algebra generated by this class E is the family, which we denote by calligraphic A here, the family of unions of any sub-collection of elements of this family. So we take any collection of indices I1 up to IM for some m, where all these indices, they are just numbers from 1 to n, and we take only the sets that have those indices. We take the union of those sets. And by doing that, we build a typical element of this class A. We also have to add another element here, which is the empty set, because then this is now an algebra which we can verify. So yes, this A is indeed a sigma algebra. And how can we see that? Well, omega is there. We just take the complete set of indices here. When we take the union, we get omega. It is closed under complements because we just need to take the complementary set of indices, and we're getting exactly the complement here. And it is closed under unions. We don't need to do countable unions because this is a finite family anyway. So when we do unions of different elements of this family, we just need to take the union of the indices here. So yes, it is a sigma algebra. Does it contain E? Yes, it contains E. We just need to take a single index here, and we'll be talking about a subset of omega given by the union of a unique element from here, which is the same as taking that element directly. So yes, it does contain E, and now we just need to check that any sigma algebra that contains E must contain all sets of this form. And of course, it must contain all sets of this form because it must contain A1, A2, A3, AN, and it must also contain A1 and A2 because being a sigma algebra, it's closed under unions, countable unions, in particular finite unions. So we can take any subfamily of events here. This will correspond to a subfamily of indices here. We can take the union, so it will have to be in A. So we check the third condition for this collection A to be indeed the sigma algebra generated by E. Finally, a very important property of sigma algebras generated by classes of events is how do we compare very conveniently two different classes. And here's a proposition: if two classes E1 and E2 are classes of subsets of the same sample space omega, and if the first class is contained in the sigma algebra generated by the second class, that's much more convenient to check in practice than doing E1 just being a subset of E2. So if we check that E1 is a subset of the sigma algebra generated by E2, then the sigma algebra generated by E1 is also at most as large as the sigma algebra generated by E2, in the sense that it's a subset of it. The proof of this proposition, as pointed out in the lecture notes, is an exercise to you.